Welcome to Part B of our digital electronics video, where we dive into the digital to analog converter, or DAC. The DAC plays a vital role in bridging the gap between the digital world and physical reality. A DAC is a specialized circuit that converts digital binary numbers into a continuous analog voltage. It's the opposite of an analog to digital converter and generates a smooth, continuous signal, acting as the final bridge to control physical devices. We need a DAC because the CPU processes digital data, but the physical world is purely analog. DACs convert binary to voltage to drive analog devices like motors, and they are essential for audio output systems to convert digital files into sound waves. The DAC process involves a three-step journey. Digital input, consisting of zeros and ones, goes through a decoder network, then a resistor network, and finally an op-amp before outputting a continuous analog voltage. First, the binary input is applied. Next, each bit is weighted based on its position, such as MSB or LSB. These weighted currents are summed using resistors to create a single, proportional analog voltage output. DAC resolution is defined by the number of input bits, N. This dictates the step size. A higher number of bits creates tinier steps, allowing the output to perfectly mimic a smooth analog curve. The number of output levels is equal to 2 to the power of n. Comparing a 3-bit DAC to a 4-bit DAC illustrates this clearly. The 3-bit DAC produces 8 distinct voltage steps, resulting in a jagged output. The 4-bit DAC produces 16 steps, which is much smoother and more accurate. There are two primary methods to build the DAC's internal resistor network. These are the binary weighted DAC and the R2R ladder DAC. The binary weighted DAC uses weighted resistors scaled by powers of 2. While the concept is simple, it is difficult for large bit counts. An 8-bit DAC requires a 128:1 resistor ratio, which is extremely hard to manufacture accurately. The R2R ladder DAC solves the binary weighted flaw by only using two resistor values, R and 2R. This architecture is highly scalable and is the current industry standard found in most commercial DAC chips. A DAC's output is a step staircase waveform because digital data changes in discrete intervals. However, the more bits the DAC has, the smaller the steps become, allowing a high-resolution DAC to perfectly approximate a smooth analog signal. DACs have several key engineering applications, including audio systems, digital control for motors, signal generation for producing waveforms, and video systems for converting graphics to analog signals for older monitors. DACs are all around us. They are in audio speakers and headphones to produce sound waves from digital data. Built-in DACs provide analog output on advanced microcontrollers, and they are used in motor control for drones and electric vehicles. In summary, an ADC translates reality into computer code, while a DAC translates computer code back into reality. ADC inputs are analog, and outputs are digital. DAC inputs are digital, and outputs are analog. These two converters are essential opposites in digital electronics. To conclude, the DAC is the crucial digital to analog bridge. The R2R ladder is the highly efficient industry standard for resistor networks, and the resolution, defined by the number of bits, determines the accuracy of the smooth analog curve approximation. Thank you for watching this video on the digital to analog converter. Keep learning and growing.